Welcome again. Today we have quite the topic. It's a big one, so I hope you're ready for it. This is all about condensation reactions, and I'm about to show you what exactly that means in this context. We're going to start by talking about the aldol reaction, in particular from the point of view of aldehydes. So you may recall from our previous lecture that I mentioned to you, you can prepare enolates effectively to completion if you use a strong base like lithium diisopropyl amide, lithium hexamethyl disilazide. Any of those things can allow you to get to the enolate in you know quantitative quantities if you perform the experiment at negative 78 degrees Celsius. And it works great for ketones, for esters, for nitriles. But then I mentioned to you that there was one tiny problem, and that was the aldehydes. The aldehydes, even under these conditions, lead to other side products. And it's because mostly the aldehyde having a lot more room available, it's a lot more reactive as well. So it just reacts with any excess aldehyde that may be present in the solution at the time when the enolate is being formed. And what ends up happening is basically what we call the aldol reaction. The aldol reaction starts by first producing the enolate, just like we talked about in the previous lecture. And this enolate, which is a really good nucleophile, sees an unreactive molecule of aldehyde and it's already going for it. Basically, the enolate reacts with this regular aldehyde, which we're going to define as a good electrophile in this reaction, um, to ultimately form a product in which these two molecules get um, bonded together. And that act of taking two smaller molecules and making a bigger one from them is what we refer to as a condensation reaction. So this is the way you want to think of it. And I know it's a kind of a weird way of describing it. The word condensation has to do with the fact that many reactions that had to do with this type of coupling, where you bring two molecules together, tended to use either alcohols or carboxylic acid functionalities, and so the endpoint will be that you will be producing a water molecule in the process of making these big molecules. And of course you will condense that water molecule later down the line, in your reflux condenser. And that's probably the origination of this word, but now we use it ubiquitously for any type of reaction where two organic molecules come together to make a bigger one. All right, so now let's get a little bit more in detail as to how this aldol reaction takes place. And by the way, you're going to find out why we call it an aldol reaction by the end of the mechanism, but let's go through that mechanism first. So the first thing is that we gotta form that enolate. So this is kind of the common ground between the lecture last time and this lecture now. You form the enolate, and notice that this time around we're using hydroxide for this. There's a specific reason for this, and mainly that hydroxide being a weaker base than it is required to fully deprotonate the alpha hydrogen, is going to produce a little bit of this enolate, right? So you'll remove that proton, the electrons will relocate to form a double bond in these positions, and you will kick the electrons away towards oxygen. You will form that enolate, but it will be a minor amount. And what this means is that the vast majority of the aldehyde that you start the process with is still going to be present in solution the moment that the enolate gets formed. So the enolate is going to see plenty of aldehyde around. So yes, it's in low concentration, and by seeing a bunch of aldehyde around, it will go ahead and react with the aldehyde. And the way it does it is by reforming the double bond. And one thing that I'm gonna recommend you to do, you're already seeing this happening here. I'm gonna label position one, the carbon where the alkoxy is positioned, the enolate, and then position two where the alkene basically ends. And after that, I'm gonna label from the carbonyl carbon of the regular aldehyde all the way up to the end of the chain, whichever chain happens to be the longest. And this will kind of help us figure out where things are going to land. But ultimately these electrons are going to come down to reform the double bonds, the carbonyl double bond. The pi electron system of the alkene is going to be attacking the carbonyl carbon of the aldehyde, and then those electrons for the carbonyl of the aldehyde will move over to the oxygen. So now, as far as determining where, how this thing is going to look, what I recommend is that now that you know it's going to take a total of 6 carbons, to kind of cover the basis of this stuff, then you can write a 6 carbon chain and label it so that you know where things are going to land, right? So label the 6 carbons, and then you start placing things in the exact spot. So position 1, for instance, that's where we're going to be reforming the carbonyl bond. So that should have a carbon-oxygen double bond. And then at position 2, we see that we have an ethyl linker that comes out from that alkene. So at position 2, we will have to have a linker. And yes, at position 3, we are changing the carbonyl carbon to an oxo group. So we have an oxo group at position 3, but yes, here is the alkyl at position 2 as well. And then that's basically the end of the story. There's nothing else sticking out from that big chain. So that's the direct product, the direct condensation product of the reaction. So the last thing that has to happen for you to isolate the molecule is to basically make it neutral. And that is to say that you will be protonating that alkoxide, right? So you will be carrying out this type of reaction in aqueous hydroxide, so that you'll have water around, and so that water can serve the purpose of donating the proton and protonating your alkoxide, right? And needless to say, you will be producing hydroxide as well. So technically, hydroxide is kind of catalyzing the process, right? And you get to this molecule, which is technically a beta-hydroxyaldehyde. It contains an aldehyde and it contains an alcohol. And if you basically take those two words together and jam them, just like uh, make an amalgam out of them, that's how you get the word aldol, right? Al for aldehyde, or technically alt for aldehyde, and ol for alcohol, right? So aldol. All right, now there's one additional feature that can take place. If you end up doing the reaction by heating it up substantially, so you're refluxing this over a prolonged period of time, something happens, something that we call the E1CB elimination. And basically what that is that you reform an enolate. So this is done under basic conditions, to be most exact. So the hydroxide you have there in solution under high heat will deprotonate. It will attack the alpha proton that you have in the molecule, the condensed molecule. The electrons will move over to ultimately produce an enolate out of this thing. So you'll have the enolate formed right here. And then what happens, and this is important, right? So this is technically a high heat type of process, is that the alkoxy group that we have up here for the enolate is going to basically go back to reform the double bond. And now notice here that I'm saying that this is the rate determining step. And that's because something very unusual is about to happen. Namely, the formation of the carbon-oxygen double bond will happen if this alkene migrates over to the next available carbon. And what that means ultimately is that this hydroxyl group is going to have to act as a leaving group. Now, when that happens, you form this fragment that is conjugated, is an alkene next to the aldehyde that we had. I would call that an enone. And the conjugation is part of the reason why this reaction is happening to this extent. But the other reason for it is that the high heating benefits entropy, right? The more you heat something up, the more you favor entropy. So notice that the molecule is basically, you start with technically one molecule, and now you're making two molecules out of it, right? So you're increasing the entropy of that system from this point of view. But this last event is the rate determining step, mostly because hydroxide is not a good leaving group, right? So this is kind of like, think of it sort of like pleading to the hydroxide, hey, please do me this solid, and just be gone. And until that happens, right, the reaction doesn't reach completion. But here's the interesting thing about it. Now, technically speaking, by all accounts and purposes, this reaction has all the features that you would associate with an E2 elimination. You're doing this under strong, or at least basic conditions, at the very least, you're doing this under basic conditions. and the attack is kind of happening all at once, except that you're kind of getting trapped initially in the enolate state, and the leaving group doesn't quite take off yet because the leaving group wasn't positioned on the section of the molecule that you were attacking. So this last step that takes the longest is the one that determines the rate of the reaction, and it's completely based on just one molecule. So it's a unimolecular process, even though it's basic, right? So that's why this reaction is not an E2 reaction, and it's definitely not an E1 reaction. It's its own thing. It's an E1CB. And just for full context, CB stands for conjugate base, as in we're forming the enolate version of that aldehyde. Okay, so with that initial introduction, I think we could stop the video right here. And on the next one, we're going to talk about how the reaction with ketones takes place. So catch you in the next video.